One of the big challenges of using design activities in the science classroom is that students lose sight of the science concepts and practices that they're supposed to be using and learning in favor of the drama of watching prototypes succeed or fail, and the very making of those prototypes tends to swamp the science ideas that you have carefully nurtured and asked them to apply when doing the design activities. The troubleshooting portfolio is a meaningful context where students can use inquiry-based observation skills, apply their science ideas in explaining what they see that's working and is wrong with their current prototypes, and then get to come up with suggestions for how to improve them.
My name is Matt Petrie, and I'm one of the authors on the paper regarding troubleshooting in the science classroom. And I teach physics at a high school where we try and use design as one of the key ways where students interact with our science concepts. And nobody's going to argue with the fact that it's the laws of science that are going to determine whether a student's design works or fails. However, oftentimes when we teach design in the classes and give students the opportunity to design, we're often frustrated with the depth of learning that occurs and how students can make random changes to designs not driven by the science concepts and maybe just stay at the surface of the big ideas that they're actually working with. So through collaboration with David Chrisman, the other author on the paper, and using the theory of informed design as a framework, we started focusing on the troubleshooting process to try and provide structure for students to apply the core science ideas and use it in their rationale to improve the design. So we want students to go through multiple iterations, we want them to observe, and as teachers we will help them observe and identify the key features and behaviors that the design is taking through a test. We then want to help them hypothesize what are the issues with the designs, what are the poor behaviors, come up with a rationale for why it's misbehaving or why it's not performing as well as it could. And then we want them to propose changes to the design that directly affect those issues and the science that's preventing the design from being as effective as it possibly can be. And over multiple iterations of that, the students will learn more about the science, they're constantly testing their hypotheses, and we see a much richer and deeper engagement with the science context.